Hello, I'm the molecular Mr. Daycock, and today I'm going to be teaching you about the exponential form of complex numbers. So, before we start, I want to remind you of a few things about complex numbers. So let's consider, first of all, our complex plane with a real axis and an imaginary axis. And we can mark these off over. Here's 1, here's 2. Assume they're evenly spaced. Here's 1, here's 2. I, obviously, in each case. And then we've got 3i up there, and so on and so forth. Now, what is a complex number? Well, a complex number is some number z of the form a plus bi, where I is defined such that I squared is equal to -1. Or, in other words, I is the square root of -1. Now, and we can do, using that information, we can plot this on here. Let's imagine we've got a complex number. So let's say our a was equal to 1 and our b was equal to 2. Then we'd have the complex number 1 plus 2i, which would be here. So the complex number 1 plus 2i is located here on the complex plane. But there's another way of thinking about it. We can think about it in terms of how far it is from 0 and how much of a turn you had to make to get there. And this is called the argument and the modulus. So the modulus of z is our length away from 0, which we can use Pythagoras to find. So it's going to be 1 squared plus 2 squared, because if we think about a right angle triangle, that's the length 1, there is length 2, and that is, in this case, is going to be equal to root 5. And the argument of z is the angle here, and the angle, well, we can think of it again in terms of a right angle triangle, so it's going to be arctan of 2 over 1, opposite over adjacent for tangent, and that will give us a number which I haven't calculated yet. Give me a moment. Approximately 60 odd degrees. Which is 1.107 radians. Okay, that's a bit quick recap on complex numbers and how they work. Let's go on a little bit further and recap just some basic numbers we've seen before. Let's talk about the number e. The number e is a specific number, and it's obviously our key exponential number. It's Euler's constant, and it is approximately 2.718. And it carries on forever. It never repeats. It's not a recurring decimal, but it is an infinitely long decimal, so it's an irrational number. We also have a number pi, which we may have heard of before, and that is approximately 3.142. And again, that carries on infinitely. It is irrational, not a recurring decimal, but an infinite one nevertheless. And these are just numbers. We can plot, and of course we still have I, which is, in some sense, the square root of -1. And we can plot these on a number line. Let's consider our number line. If we've got a number line, we've got 0, we've got 1, we've got 2, we've got 3, we've got 4, etc. Well, we've got e is about here, pi is about here, and the square root of -1 is about here. So these are our numbers on our number line in arguably interesting places. Now I'm going to tell you a very interesting fact about these three numbers. and it's called Euler's identity. And given what we're thinking about in these terms, given what these numbers are, this should seem absurd. But it is 100% true, and by the end of this video I will have proved it. And this is it. This is Euler's identity. E, which again is about 2.7, to the power of pi, which again is about 3.14. So we're currently looking at about 2.7 cubed-ish, multiplied by I. So the I is being multiplied by the pi. So e to the pi I is equal to exactly, this is not an approximation, is equal to exactly -1. And as I say, you should look at that and go, that's nonsense. It doesn't make any sense whatsoever. 2.7 cubed, that's going to be what? Around 12 or 15-ish. And then just because that's also to the power of I, suddenly we get -1. Doesn't make any sense whatsoever. But it is 100% true. So, to see that this is true, we are going to go to Maclaurin series again. And I am going to write out, first of all, the Maclaurin series for cosine of x. So the Maclaurin series of cosine of x is 1. I'm going to leave a bit of a gap, plus, because we think of this is the 0x, there's no x's, as it were. So I'm just going to leave the gap for the x's, plus x squared over 2 factorial, and I've already got that slightly wrong. It's minus x squared over 2 factorial. Then I'm going to leave a little gap for the cubes, and it's going to be plus x to the 4 over 4 factorial minus ... That's obviously x to the 6 over 6 factorial, and so on. And then I'm going to write out the Maclaurin series for sine of x, and that's going to be equal to x to the power of 1 over 1 factorial minus x cubed over 3 factorial plus x to the 5 over 5 factorial, and that carries on forever as well. Now, lastly, I'm going to write down the Maclaurin series for e to the x. And this is 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4 over 4 factorial plus x to the 5 over 5 factorial plus x to the 6 over 6 factorial. And what you should see immediately, and of course it carries on forever, is how well this matches up almost exactly with cosine and sine. Except for one unfortunate detail. Although these here match up perfectly, and as do these here, these ones in the middle here, the x squares and x cubed, have different signs. And the same, the x to the 6 and the x to the 7 will have different signs. So for cosine and sine, they're negative, but for the e to the x, they're positive. And this is a pattern of order 4. It switches every 4 terms. So what we need is something that switches from positive to negative, not every other time. Like what we might think, oh, e to the minus x, that'll work nicely. But actually e to the minus x will swap every other power rather than every power. We need every 4 powers. We need something that switches every 4 powers. And that is precisely I. So what we're going to actually write out now is e to the ix, and see what that is in terms of its Maclaurin series. Well, it's going to be 1, the 1 stays the same, plus ix over 1 factorial, plus ix squared over 2 factorial, plus ix cubed over 3 factorial, plus ix to the 4 over 4 factorial, plus ix to the 5 over 5 factorial, and so on and so forth. Which is then 1 plus, well, ix over 1 factorial, that's fine, plus I squared x squared over 2 factorial, plus I cubed x cubed over 3 factorial, plus I to the power of 4 x to the power of 4 over 4 factorial, plus I to the 5 x to the 5 over 5 factorial. And why is this helpful? Well, in fact, we need to remember what I squared is. I squared is negative 1 by definition. I cubed is that times I, so it's negative I. And I to the 4 is that times I, which is, well, it's I squared squared, which is just 1. So using that information, we'll plug all this in. We get 1 plus I lots of x over 1 factorial. And then I squared is negative, so we get minus x squared over 2 factorial. And then we get I cubed is minus I, so we get minus I lots of x cubed over 3 factorial. And then we get plus again, because x to the 4 is, I to the 4 is 1, so we get x to the 4 over 4 factorial. And then we get I to the 5, the pattern is going to start repeating. We get plus I lots of x to the 5 over 5 factorial. And now things match up perfectly. We have the positives and the negatives in exactly the right places. And the only thing that's a little bit odd is that we have these i's in front. So what we can do is we can write e to the ix is going to be equal to, and let's gather the terms that we want to be together. So 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial plus ... although that's minus at that point. And here we've got this extra term of I, so I'm just going to factor that out at the front. Plus I lots of x over 1 factorial minus x cubed over 3 factorial plus x to the 5 over 5 factorial, and so on. And what do we have here? Well, this bit is the Maclaurin series for cosine. And this bit is the Maclaurin series for sine. And so we've got that e to the ix is equal to cosine x plus, and don't forget this in front, I sine x. And this here is an incredibly important formula for complex numbers. Or in fact, let's write it using some nice colours. E to the ix is equal to cosine of x plus I sine of x. E to the ix is equal to cosine x plus I sine of x, and that has just been proven here with these Maclaurin series. And if you want to go over that again, pause the video, go back a bit, look through it again, see that it makes sense. If you're not sure about the Maclaurin series, you can watch my video on that, or in fact prove some of them yourself fairly easily using that information. Okay, and this is Euler's formula for complex numbers, and it is incredibly powerful. Primarily because it allows us to write complex numbers in different ways. Now, let's consider what this is saying here. First of all, if this is a complex number, what's the size of it? What's the modulus of it? Well, the modulus of it is going to be the square root of cosine squared x plus sine squared x, which is the square root of 1, which is 1. So the size of this complex number of, if I've got a complex number of the form e to the ix, the modulus of it is always 1 for every single possible value of x. What about the argument? Well, the argument of it is going to be, well, it's the argument of this, so it is going to be arctan of, well, we need to think about this in terms of what's going on in terms of our triangle. Well, our I side is sine, our real side is cosine, so it's going to be arctan of sine x over cosine x, or it's going to be arctan of tan of x, which is just x. So, if we have a complex number of the form z equals e to the ix, then the modulus of z is always 1, and the argument of z is just equal to the x we had at the top, which leads us to suggest, in fact, maybe we should write it as e to the I theta instead, because we'd actually, in fact, this x value here is an angle. It's the angle it makes in the Argand diagram with 0. And then that leads us a little bit further. What if I were to take multiples of this? If this is always 1, well, if I were to just multiply it by something, let's say I was going to call it a complex number z equal to r e to the I theta. And remember, at this point, we care about r and theta being entirely real. Well, then the modulus of this is going to be equal to the modulus of r e to the I theta. In fact, we really want the, no, not necessarily positive reals, but generally reals. And that's going to be equal to, that means the modulus of z is going to be equal to the modulus of r multiplied by e to the I theta. And given r is real, and in fact we'll pick r as positive, so we'll say theta is the number of reals, we'll say r, we want to be a member of the positive reals, then we'll get modulus of z is equal to r times by e to the I theta. Or the modulus of z is just r, because e to the I theta is 1 every time. The modulus of it is 1 every time. So in fact, if we have a complex number, and this is absolutely incredibly key, if we have z equal to r e to the I theta, then the modulus of z is r, and the argument of z is theta. Okay, we're now going to use this information. Taking a little bit of a while to go through, but let's just do some examples of converting one way and the other. So, if we have z is equal to 1 plus root 3i, well, we want to write it in the form of z equals e to the r e to the I theta. Then we just need to rewrite this slightly, and we'll end up with, we just need to, in fact, remember what these are. This here is the modulus of z. This here is the argument of z. So we just need to work those two things out. So the modulus of z is equal to the square root of 1 squared plus root 3 squared, which is equal to the square root of 4, which equals 2. And so our r equals 2. And the argument of z is going to be equal to arctan of root 3 over 1, which is going to be equal to pi over 3. And so, writing it in this form, z is equal to 2 e to the I multiplied by pi over 3. And that's all there is to it. Let's have a look at this one. Same thing again. Z equals r e to the I theta. So the modulus of z, so r equal to the modulus of z is equal to the square root of -2 squared plus -2 squared, which is equal to the square root of 8, which is equal to 2 root 2. And the argument of z is equal to arc tan of -2 over -2, which is equal to pi over 4. Now, this is where we need to be careful because this is wrong. Modulus absolutely fine. This argument that we've worked out here is wrong. I want you to take a moment, pause the video, perhaps think about why. Why can't it be pi over 4? And the answer is, we need to think about our Argand diagram. -2 minus 2i is down here. But we've worked out the argument here. And remember, arctan arguments repeat every pi radians. So in fact, we just need to subtract pi radians from it. And here the argument is minus 3 pi over 4. So, and that is another valid inverse tan of -2 over -2. So we're dealing with arctan is minus 3 pi over 4. And that gives us our final answer is z is equal to e, let's not forget the modulus, z is equal to 2 root 2 e to the minus 3 pi over 4i. I'll actually cut through some of the lines there. Right, and then lastly, what about if we have to turn the other way? Well, we know that z is going to be equal to, well, 4e to the pi over 6i, but we know that e to the I theta is equal to cosine theta plus I sine theta. So I'm just going to plug that in and here, and we get z is going to be equal to 4 lots of cosine pi over 6, because our theta is of course pi over 6, plus I sine of pi over 6, which gives us z is equal to 4 lots of cosine of pi over 6, it's root 3 over 2, sine of pi over 6 is just a half, and then we just need to expand and we get z is equal to 2 root 3 plus 2i, and we're done. Okay, so there you go. That's 3 examples of how you can convert back and forth between the exponential form of complex numbers and the standard a plus bi form of complex numbers. And if there's anything you need to take away from the video, it is this formula here, 100% incredibly important, and this connection here between the modulus and argument and how they connect to r e to the I theta. So those are the 2 things you should definitely think as your takeaways from this video. This has definitely become quite a long one. Thank you for watching. If you still are, hopefully that was helpful to you.